Good afternoon, everybody. Again, we have another very excellent seminar from a very knowledgeable speaker, Dr. Marjan Popovski. He's a lead scientist in the building system group at the FPInnovations. He's also an adjunct professor at University of British Columbia at UBC and the Center for Integrated Wood Design at the University of Northern British Columbia. Marjan has over than 30-year experience in research and technical experience in the areas of seismic performance of building. He is one of the leading researchers in the area of seismic performance of wood structures particularly, which is the topic of today's presentation. He is an author and co-author of over 180 scientific and technical publications, including textbook chapters, the Canadian Technical Guide for the Design of Tall Buildings, and the Canadian and US CLT handbooks, and the Canadian Technical Guide for Mid-Rise Wood Frame Construction. He is part of the research team that has developed the seismic design factors for platform type CLT buildings in Canada and in the US. He's member of He's member of the technical committee of the Canadian Standard for Engineering Design in Wood, CSA 86, and also sits on various Canadian, US, and ISO committees. He served also on the National Building Code of Canada on the Committee for Earthquake Design for 5 years. So again, please welcome with me Dr. Popovski, please. Okay, Miriam, it's your floor now.
Thank you so much for the kind introduction. Good afternoon, everybody. My talk today will be related to expanding the market for mass timber buildings through research. And what I will try to do is basically to explain what research we are doing related to wood buildings in general at FPInnovations. First of all, probably all of you are not familiar with FPInnovations. So FPInnovations is the Canada's Forest Products Research Institute. It's a private non-profit institute that specializes in creation of solutions in support of the Canadian forest sector global competitiveness. It's a Canadian public-private partnership, and it's a partnership between the federal government, provinces and territories in Canada, and industry members. We have approximately 450 employees and around 170 industry members. We have 3 main laboratories in Vancouver, Montreal, and Quebec City, and our research budget is around $65 million a year. We basically provide the optimized solution to maximize the values from the industry, all the way starting from intensive silviculture, then forest managing, to processing, transportation, primary and secondary manufacturing of wood products, all the way to the building systems. Because most of the wood products that are produced, they end up one way or the other in structures and building systems. So that's the group that I am in, the building systems group. We're kind of like on the top of the food chain in our organization. We basically do lots of collaborative research and development between government, universities, and the industry together. In the building systems group, most of the research is related to these main topics: mid-rise wood frame construction on or without podiums, mass timber buildings, tall wood buildings, wood hybrid systems, resilient structural systems, and industrialized construction. Our group, the research in our group is from a multidisciplinary approach. We also kind of like a holistic approach to the solution. So not only the solution has to be good for structural and seismic performance, but also it has to be good for the serviceability performance, for the durability and energy efficiency, for the fire performance, acoustics, and then of course to be a sustainable solution. So we look at the holistic approach when we are doing our research. I know this might be some new to you, but this is probably the only way to go forward, because if we only provide a solution that is only good for structural performance, but it's not good for other performances, then we basically have not done much to introduce that solution in the market and to get accepted in the codes. So let's start with some of the research that we've done on the structural and seismic performance. And I'll talk here about mass timber seismic force resisting systems. So the seismic forces that basically are generated on the structures, they have to be taken by the seismic force resisting systems. And we have many such systems in timber structures. For example, such as platform type mass timber walls, balloon type or cantilevered single or coupled walls, brace timber frames, moment resisting frames, and many different hybrid steel, wood steel and wood concrete system. And finally, we also have innovative hybrid or resilient systems. Each of these systems has numerous components which behavior needs to be quantified. So we started our research on mass timber systems starting the platform type CLT buildings. We did numerous tests, dozens of tests on 11 different types of CLT walls that can be used on platform type construction. For those who are not familiar for platform type construction, that's a construction where basically the height of the wall is basically equal to the story height. So you build the walls on the first story and then you put the floors on the top of the wall, and then you put the wall of second story, and then you put the floor. So basically, the floor at each story serves as a platform to building the next story up. So we did tests on quasi-static tests to determine the seismic performance of different types of walls, as you can see here on the slide, from walls with hold downs and shear anchors to walls with openings to walls with vertical joints between them to single story and two-story walls. And we use different fasteners from screws, glue-lam rivets, self-tapping screws, nails, and so forth, and using different connector brackets, as you can see on your slide. What we found out is that connections definitely govern the performance, seismic performance of the walls. So for example, if you use a CLT wall with screws connected to the floor below, they can provide a connection with significant stiffness. However, the ductility of such connection and the energy dissipation of such connection is pretty low. On the other hand, if you use walls with hold downs, then as you can see at the bottom, then the performance of the wall significantly improves in terms of seismic performance and energy dissipation. We also tested a two-story CLT house, 6 by 4.8 meter in plan. And basically that house was symmetric in one direction and unsymmetric in the other dimension. So we did quasi-static testing in both directions to determine basically how a 3D structure would perform under lateral loads. And again, lots of findings here. Of course, every of these slides can be a presentation on its own. We found that the structure responds on the combination of rocking and sliding deformations. Main deformations, again, they were in lap joints between the CLT panels, in the brackets connecting the walls to the floor, and in hold downs. However, the structural integrity was not compromised at failure, and we were able to get up to 3.2% drift at the bottom story. So the hysteresis loop at the left shows basically the performance of that house at the bottom story, and on the right, you have the performance of the second floor of the house. As you can see, and as expected, the most of the deformation and energy dissipation occurred at the bottom story of the house. The deformation of the CLT house basically consisted of many different components. We had a clear rotation component of the wall on the first and the second floor, then a rocking component at each floor, then sliding at each story of the walls at each story, and finally in plane wall deformation that consists of bending and shear deformation inside the panels themselves. Then having all of this data from the experimental test of single walls, the 3D house, and some data available from other researchers. We did a long, comprehensive analytical study to determine the seismic modification factors for platform type CLT buildings for implementation in National Building Code of Canada, NBCC. So we did the modified FEMA P695 analytical program. This was done in collaboration with Colorado State University and Texas A&M University. And we did develop numerous archetypes for CLT walls in platform time construction with different heights. We also modified the procedure to serve the Canadian sites such as Montreal, Vancouver, and Victoria. And of course, we chose and scaled different earthquakes coming from 3 different sources. On the West Coast, subduction, crustal, and subcrustal earthquakes, as well as local earthquakes for Montreal. And out of all that analysis that took more than 2 years, we were finally able to introduce the platform type CLT walls as a seismic force resisting system in 2020 National Building Code of Canada with the seismic factors of RD of 2.0 and ROs 1.5. For those who are not familiar, those R factors basically quantify the ductility and energy dissipating capability of the wall, of the system. And in the National Building Code, there's a table with the SFRSs, the seismic force resisting systems with their R factors for concrete, steel, and wood buildings, as well as masonry buildings. So we were able basically to also establish height limit for the system. So the height limits are 30 meters for low and moderate seismic zones and 20 meters in high seismic zones, which will be seismic category 3 and 4 in the 2020 NBCC. Based on the research that we've done, actually, also we implemented CLT as a system in CSO 86, which is the Canadian standard for engineering design in wood. And that was first done in 2016. And then in 2019 edition, we did significant revision of those clauses based on the research that was conducted at FPInnovations and other places. Next system we are looking at this point is brace timber frames. Brace timber frames actually can be one of the most efficient seismic force resisting systems. They are frequently used in mid-rise and tall buildings. And why they are used is because they provide high stiffness for the building. And however, the ductility of the brace system can sometimes be limited. You have examples there of brace frames being used in real buildings, in UBC's Earth Science Building, which is a 4-story building here at University of British Columbia campus, and the 18-story Brumunddal building in Norway. So what is the reason for this research? As I mentioned already, and you've seen some examples, brace timber frames were included as a SFRS in NBCC with their R factors. However, we don't specify in our 086 standards how we can achieve those R factors. So what you see here on this slide is basically a part of the table of seismic force resisting systems for brace timber frames in NBCC. So you can see here we have braced or moment resisting frames with ductile connections, and we have 2 ductility levels, moderately ductile brace frames and limited ductility brace frames, and the RD factor is 2.0 and 1.5 respectively. However, the NBCC refers the designer to go to CSO 86, which is the wood design standard, on how to design these brace frames for the certain R factors given in the code. However, unfortunately, we don't have those design guidelines. So the idea behind this project was to quantify the seismic performance of brace timber frames and prepare design guidelines for 086, and basically also prepare guidelines which connection can be used in a brace frame with which RD factor. So also what was part of this research project was to identify which connection should be used for moderately ductile and which one for limited ductility categories, and then also check the height limits for brace timber frames and which connection can give you which height limit for different types of brace timber frames. So it's a complex problem, and We started from testing, of course, connections. In timber brace frames, all the deformation capability comes from the connections at the both end of the braces. So basically, we tested braces with reduced length with connections at the both ends, as you can see on the left side. And then, we obtained the hysteresis loop and the performance of each of these connections. So the hysteresis loop on the right is typical performance of a brace frame with a riveted connections at both ends. Then, having this information, we built numerical models to predict the response. The numerical models of brace timber frames with riveted connections were developed for single-story and multi-story buildings, for buildings designed with RD equal 2.0 and RO equal 1.5. And we used different building heights and aspect ratios in our analysis. So you have example there of a single-story brace frame where it can be used in industrial construction, commercial construction, and so forth, as well as on the right, a multi-story brace frame that can also be in residential and commercial construction. We used 2015 NBCC approach for selecting and scaling of ground motions and for conducting the dynamic analysis. In total, we had 15 earthquake ground motions, 5 earthquakes from each type, crustal, subcrustal, and subduction earthquakes for locations such as Vancouver, BC. And preliminary results told us that basically the RD factor of 2.0 and RO of 1.5 can be appropriate for brace timber frames with riveted connections. And also the height limit in high seismic zones can be increased from 20 to 30 meters. Again, these are just preliminary analysis. We have another 2 years to go in this project. We will build a very comprehensive modeling strategy and very comprehensive analysis on many different types of brace frames with many different types of connections. And basically that will serve, that technical information that we get will then go to the Standing Committee of Earthquake Design for either increasing the height limits for the brace timber frames or changing some R factors is needed, or adding new brace frame systems with increased RD factors if such solutions are found and proven by the analysis. Then further on, we went and basically what is important for every system, every SFRS, is basically to find the link between the connection ductility, which we call local ductility, and the global ductility or the system ductility. So we started doing work in this area as well, and we started for very simple brace frames. Basically, you have your brace consisting of the wood part of the brace, which is or stiffness-wise, if you see on the figure, so K brace, and then you have K of the connections on both sides of the brace. And then basically you try to establish the relationship between how is the connection ductility and performance related to the system performance. And we went with some iterations, and we obtained the formula where the relationship between the connection ductility or mu brace frame basically is a function of the ductility of the connection 1 plus the ductility of connection 2, and also a function of the stiffness ratio between the connection and the axial stiffness of the brace itself. So once we developed these equations, we did pushover analysis on brace timber frames using numerical models, and we showed that the equations basically can perfectly predict the system ductility within 5%. So that was pretty good for us. Then we also developed conservative relationship between the RD factor, as it is in National Building Code of Canada, and the ductility of the connections and the stiffness of the braces. And basically, we found out that in order to obtain moderately ductile brace frame with RD factor of 2, we have to have 11.5 ductility in the single connection or 6.3 ductility in both connections. For the RD of 1.5 or limited ductility category brace frames, the single connection should have ductility of 5.4 or both connections to have ductility of 3.2. Again, these are simplified solutions, and the true relationship between the local ductility on the connection level and the global ductility on the system level can only be done through a comprehensive nonlinear time history response. And that's what we're going to do. So this was just done as a preliminary work to basically see and feel the problem and basically choose our spectrum of analysis where we should focus on. Next system that I'm going to talk about are balloon mass timber walls. Those walls are very similar to reinforced concrete or steel shear walls. Basically, these are the walls that go all the way along the height of the building from the foundation to the top of the building. They are already being used as an alternative solution in some mid-rise buildings, such as the Origin and Arbora buildings in Quebec. These are 8-story and 30-story buildings, CLT buildings. And the behavior of these walls is highly influenced by the wall material and the connections at the bottom of the wall. So the goal of this project was basically to develop the missing information on the seismic performance and then again codify the system. All the research, I'm sorry, I have problem moving to the next slide. Okay, here we go. So to quantify the performance of these balloon walls, we did testing in our Quebec laboratory, many different types of balloon walls. So as you can see, on the left, we have a single balloon wall with hold downs only. Then in the middle, you have a balloon wall with hold downs, but also with splice connections. So basically, this wall has two panels. So panel on the left and panel on the right. And then you have splice connections along the height of the wall. And then the wall number 3 here is also consists of two panels. It has a hold down connections, but also a stiff connectors between the walls. So we wanted basically to investigate how these connections between the wall panels along the height will influence the response of the wall. And again, what we found out is, of course, they have different responses, the single walls versus coupled walls, and again, differences between coupled walls as well. Again, all of these testing programs can be a presentation on their own, but I just wanted to mention and give an overview at this time of our research program. And again, this is a typical hysteresis loop that we found from cyclic tests on balloon walls made of X-LVL, which is cross-laminated veneer Lamble walls. So this is another mass timber product that has high potential in this application. And we found out that basically these products, as well as the connections that we tested, they're really suitable for application in the buildings. The research on this project, the same as on the braced timber frames, continues, and the end results are expected to end with basically implementation of this system in National Building Code of Canada. So that way, basically, for this system to be really approachable and easily understood and taken by the designers for real buildings. We also did some innovative testing on innovative connections to be used in these balloon walls. For example, here you have a connection that basically has a square opening inside of the CLT panel. And we have a steel plate that is inserted in that opening, and that steel plate is connected to the foundation with steel rods on both sides of the CLT panel. And then by changing the end distance between that hole and the end of the panel, you can definitely obtain different response of the connection. So we did investigation in these types of connections as well, and we found that different end distances provide different performance levels. And from there on, basically, we can also implement this connection in our analytical study when we basically start to quantify the response of the walls. On the analytical work, we already developed analytical models based on engineering principles in MATCAD, again as a preliminary. And then those models were validated based on the test results. and the influence of key parameters on the structural performance of the walls was investigated, such as the pattern of the lateral load that basically is on the wall, the vertical load of the walls, the aspect ratio of the panels, what connections are needed, and so forth. So you have many different parameters. So here you have basically a balloon wall that consists of 2 panels, and each panel has a hold down, and you have these splice connections between the panels. So basically we were just investigating, because this is a new system, completely new system, not much information is out there. So basically we are kind of like trailblazers and trying to basically investigate the performance of these systems from scratch. Again, as I mentioned, the research on balloon walls continues, and the objective is to basically, in 2 to 3 years, gather enough technical information and enough for implementation in National Building Code of Canada. Some of our research was also related to tall wood demonstration buildings in Canada. Probably all of you are familiar. For those who are not familiar, in 2013, NRCan, National Resources Canada, which is a department in federal government, launched the Tall Wood Buildings initiative. And out of that initiative, 2 tall buildings were built. The 18-story Brock Commons building at the University of British Columbia here in Vancouver, and the 13-story Origin building in Quebec City. The Brock Commons building, as you probably all know, it's a hybrid one. It consists of concrete shafts to basically they're taking the lateral loads, which are the wind and seismic loads, while the gravity loads are taken by mass timber floors and mass timber columns. What was innovative for this vertical load system was that the load from the column above the floor was directly transferred through a steel pipes here, as you can see, to the column underneath. So basically, the floor doesn't see anything from the force coming from the floor above. That way, basically, the force is transferred directly from the column on the top floor all the way to the column at the bottom floor. So this basically enabled us to position the CLT floors on each column and provide what we say point supported floor system. This floor system was first time used in this building in the world, because most of the CLT floor systems before this one were basically as a support, they used the walls with sufficient length. So you have basically your wall panels, and then you have your floor panel at the top of the wall panel, and you have sufficient length basically for your floor panel to sit on. But here your floor panels are only sitting at the points in the corners. And this, by the way, this innovative solution was developed by Fast and App design engineers from British Columbia here in Metro Vancouver. But also what this floor allows is basically to use the CLT panels for bending not only in one direction, but also in the other perpendicular direction as well, because you're only supported by 4 corners of the panels, so you have bending in both directions. So that was something new that was basically never investigated. And we basically helped the designers for this project by conducting tests in our laboratory on 18 different CLT floor solutions with different thickness, different number of layers, different thickness of each layer, so forth. Floors with openings, as you can see here, there's an opening in one floor for services, floors without opening, and so forth. And basically what we obtained is, as you can see here, not only the panel is bending in this direction, but it's also bending in the perpendicular direction. So based on our results, we were able basically to provide the designers for the tall wood building here at the UBC with the best solution for the floors, and that solution was basically implemented in the real building. I'll now switch a little bit to needs for low damage structural systems. Those who are familiar with earthquake engineering and earthquake performance of building, we have realized that life safety alone is not good enough criterion if it doesn't account for the economic losses of the building. So economic losses can be such as building operation and damage, and they sometimes can be higher than the cost of the building itself. So there is a need definitely for what we call resilient or these low damage structural systems that can not only reduce the damage while offering also the higher level of safety to the occupants. And one system, such system is the post-tensioned rocking, controlled rocking wall system or frame system called PRES-LAM. So this PRES-LAM system was developed originally at the University of Canterbury in New Zealand, and it can be implemented in moment resisting frames, shear wall systems, or combination of those. And the main components are mass timber walls, beams and columns, and anchored post-tension cables or rods, and energy dissipation devices. FPInnovations actually has purchased the licensing rights for this system for the Canada and the United States. Here is an example of the PRES-LAM concept in frame applications. As you can see, you have moment resisting frames consisting of mass timber columns and beams. And the moment resistance in the joints is basically obtained by having these post-tensional rods, which are given here in yellow. So those potential loads provide compression at each story, and basically that gives the moment resistance at each of these joints, column to beam joints. Additional resistance and energy dissipation is coming from axial dissipators that are placed in multiple places along the structure, and that's how basically you get your energy dissipation. In the wall applications, you can see here balloon walls, again, with post-tensioning cables, which are given in yellow here, and you have U-shaped flexural plates between the walls. So what is happening basically when these walls start are submitted to lateral loads here, you have basically the post-tensioning cable here, not only providing resistance, but also providing self-centering ability after the end of the earthquakes, while the dampers provide the energy dissipation. So the result of the performance of this wall is a combination of the this nonlinear elastic performance of the cables, plus the energy dissipation of the dissipators. And so the combined system can have this type of flag-shaped hysteresis loop. We did lots of research on these systems as well. So we did a total of 17 different tests using Canadian CLT, with single walls, with axial dissipators or fuses, or coupled walls, as shown here in the slide, with U-shaped flexural plates. And we investigated various parameters such as influence of axial load, location and number of fuses, and so forth. And we found that, of course, all of these parameters influence the response. For example, here you can see on the left is the response of a wall with a certain level of axial post-tensioning force. On the right is also the wall with different level of axial force, but also different positioning of the axial dissipators. So how you basically, it's a complex design of these systems, so every parameter has to be taken into account. We also did numerical models of these walls to quantify their performance, and these numerical models will be used basically to try to quantify even more the seismic performance of this system and provide solutions, technical solutions for the designers in Canada and the United States. Here are some results that we obtained from the numerical models. I will not go through the details, but what it shows here, every line, is that every parameter you basically change, it has influences on the response, and how that influence has to be taken into account when you basically have the behavior of the wall. We were also part of the consortium of research organizations, universities and institutes that conducted in 2017 a two-story building was tested at the shake table at the University of San Diego. This was post-tensioned rocking wall system, so the PRES-LAM system. As you can see here on the left, you can see the two-story building being tested. You see two vertical walls and two floors. And on the right side, you have a close-up view at the wall. So you have two post-tensioning cable on each wall, and then you have UFP plates between the wall. And here is a close-up view of one UFP plate connecting the two walls. So the shaking table test on this building showed that absolutely the building suffered no damage. Numerous types of shaking table tests were conducted, no damage at all. So the building can be used basically after a major earthquake. We are also part of the continuation of this project. Right now, the design is being worked up for a 10-story PRES-LAM building that will be tested at the same shaking table in San Diego. For the summer, it was planned to be done this summer, but due to known reasons, we were not able to test it this summer. It will be conducted next summer, 2021, at the University of San Diego. This will be the largest, the tallest timber building tested on a shake table in the world. And we are really glad that basically the consortium of US universities choose this post-tensioning and controlled rocking system as a choice for their seismic force resisting system. First building that used this system in North America was the Forest Science Center at the Oregon State University. So here you have some construction photos of that building. You can see here the end of the post-tensioning cables and the steel plate basically at the end of these post-tensioning cables, same here. And you have a photo of the building in construction. That building is now completed and it's really a magnificent building. My plan was to visit this building in March. However, due to COVID situation, I had to cancel my trip. As I mentioned, we collaborate with many universities, and I'm pleased here to mention that we had a very, very successful collaboration with the Western University. We basically have a 4-year joint research project between Western University and FPI to take the advantage of your amazing facilities of wind tunnel and having a very gifted PhD candidate, Matthias Bezabec. So probably he presented his research already to the faculty and staff. So I just wanted to mention here that Matthias, led by Girma and Solomon from UBC Okanagan, basically they did amazing work. First time in the world, basically they did wind tunnel test on 40-story tall mass timber building at the boundary layer wind tunnel laboratory. They did this high frequency pressure integration test setup. Basically you see the HFPI model on the right here. Not only that, they did also wind tunnel testing of the 18-story Brock Common building that is been built here, that was built in Vancouver, the tall building that I talked about, and also try to investigate the surroundings of that building. So from an aerial view here, basically here is the building and you see the buildings around. So they build a model in the wind tunnel of the building itself and the building surrounding that building. They've done tremendous analytical research as well. Again, this is breakthrough research, first in the world, that basically quantifies the wind performance of tall wood buildings. And the results from this study will really be very, very beneficial, not only to designers and researchers in tall wood buildings as well. So thanks again, Matthias, Girma, and Solomon for this wonderful collaboration. With Solomon Tesomarian from UBC Okanagan and Matthias Bezabec again, we were able to develop an innovative steel CLT hybrid system with innovative connections, and basically to define the energy-based damaging indexes for these types of building. So we developed also the force and performance-based design guidelines for this system. Basically, the system contains of a steel moment resisting frame, but not high ductility steel frame, but lower ductility steel frame. And then in the base of that steel frame, we inserted CLT panels with the connections that can dissipate energy around the perimeter of that panel. And basically those, by changing the gap of that connection and the properties of that connection, we were able to basically change the force and deformation properties of the system. With the UBC here in Vancouver, we also worked with Dr. Tanner to touch the issue of disproportionate collapse in mass timber buildings. Again, there's lots of research on this topic in concrete and steel buildings. Unfortunately, not much done in mass timber buildings and wood buildings in general. So again, this research was very, very beneficial for the designers and researchers in this area. So far what I've mentioned was all structural and seismic. As I mentioned, our group has multi approach, holistic approach to our research. So the fire part of our group staff is basically developing knowledge base to support alternative solutions and code changes for wood-based solutions in terms of fire performance, and provide designers with variety of mass timber options that can meet or exceed the fire requirements, and give confidence to the authorities having jurisdiction, such as cities as well, that the mass timber buildings can meet or exceed the safety requirements by the code. So throughout the last few years, we've done tons of research in this area as well. We obtained the fire resistance of cross-laminated timber, nail-laminated timber, dowel-laminated timber, glue-laminated timber, cross-laminated LVL, and timber concrete composite floors. And we proved basically that they can achieve the fire resistance of higher than 3 hours and the charring rate approximately 0.65 millimeter per minute. We also developed calculation methods for fire resistance, and we also developed how basically is the fire performance of fire stop around penetrations in mass timber, and proved that they can basically meet the 2-hour fire rating. In the fire-related research, I want to mention that we also improved the fire performance on many mass timber products by using encapsulation methods or gypsum boards, applying gypsum boards. Then also we did research on fire spread in voids and in mechanically laminated timbers. We also did fire testing on different adhesives that can make the CLT products, so that basically this product can meet the requirements of the PRG 320, which is the CLT material standard. And we also did research on the fire spread in the floor voids with exposed mass timber and dropped gypsum ceilings. Other aspect of research in our holistic approach is the floor vibration and noise control. Again, you can provide a perfect structural solution, but if that solution it doesn't meet the criteria for floor vibration or the noise control of the building, you haven't done anything, right? So you don't want to disturb your grandma while reading while you walk on your floor. So just as an information, the noise basically in a building can come from 2 main sources: impact noise, as is given here in the figure, or as airborne noise, either from inside or outside the building. So that airborne noise then can be transmitted through the walls in the nearby part of the building or nearby room, or can be transmitted what we call the flanking, through flanking, by using the ceiling or the floors from the story above and below. So we developed a new method for determining the CLT floor vibration and implemented that method in CSA 86, which is again the engineering design standard for Canada. Now we are working on extending the OET6 CLT floor design method to include a broad range of other different mass timber floor slabs. We will also consider concrete topping, multi-span continuity, and different floor support conditions. We also evaluated the performance of dowel laminated timber, or DLT, as you can see on the figure here. And this evaluation of the floor performance can be done in many different ways. Of course, you can use sophisticated measurements and instruments and accelerators and so forth. But also you can done a low-tech but very useful tests, like somebody walking or jumping on your floor here, while somebody else is sitting, and basically seeing the comfort zone of the person that is just inside that room, and how is the feeling of a real person for those floor vibrations. We did we monitored the Brock Commons building, and we measured not only the building but also the floor vibration of this building where it was being built during construction and after construction. So we determined the mode shapes of the building, and here we are basically on site during the construction measuring the floor vibration of that building. In terms of acoustics as well, acoustics in the codes is usually characterized by two parameters, impact insulation class or IIC and airborne sound insulation performance measured by apparent sound transmission class or ASTC. And basically in our research, we developed different solutions for different mass timber products with topping, concrete topping, without concrete topping. And we provided these numbers because these are the numbers, the IIC and the ASTC numbers are used in the code for to determine which solution for the flow is acceptable and which is not. So there's minimum of IIC class and AST class that the floor has to basically have in order to be permitted to be built in the building. Also, we monitor wetting and drying performance of the different wood products. For example, we are monitoring the 29.5 meter high Wood Innovation Center in Prince George, BC. So what we found is that the wood moisture content changed from 30% during construction to 5% in service during the winter. That the glulam columns and CLT walls showed minimal shortening due to change in moisture content. And the roofs with built-in interior ventilation, they function were able to really dry fast the wetted parts of the building. We are monitoring the moisture content of the floors at the UBC Brock Commons building as well. And what we found that since the CLT floors stayed below 18% moisture content before the topping was installed. So you can see here basically the moisture content at each floor of this 18-story building. We also do testing on on-site protection measures to basically protect the wood products from water. So what we found is that the water is penetrating slow from wide surfaces on the products. Exposed end grain is very susceptible to moisture absorption and penetration. And the end grain sealer was found to be very effective. Wet concrete topping did not cause considerable wetting on the product, and timber, of course, should be kept dry before and after installing any covering material, including the fire protection. So finally, we prepared at FPInnovations several multidisciplinary guides and handbooks, and those handbooks, I have to say, they created a paradigm shift in applied research, development, and deployment of wood buildings in general. And we developed these handbooks and guides, again, collaborating with universities, with National Research Council, with provinces, NRCan, the industry, and NSERC as well. So in 2011, we published the Canadian CLT handbook. This was the first handbook for CLT buildings in the world. Second edition was released at the end of February this year. It consists of 2 volumes. It's over 700 pages of state-of-the-art knowledge, research and design information related to CLT structures, again, from structural performance, seismic performance, acoustic performance, fire performance, durability performance, and so on. So if anybody is interested in this handbook, it's free for download, and you can find here the website. Basically, you can download your handbook from. The French version of this handbook will be available shortly. In 2014, we also published, first in the world, the technical guide for design and construction of tall wood buildings. Right now, as we speak, we are working on the second edition of this guide, which will be published in September 2021. And I'm happy and proud to say that Western University staff was also involved in drafting the WID performance and design section of this guide. And I use this opportunity to thank Matthias and Girma again and Solomon for their help on the drafting this chapter. We also developed a timber concrete composite floor guide. This guide was published in February 2020. And the information of this guide will basically form the design, the technical information in this guide will form the basis for implementation of new criteria for these floors in the Canadian standard for wood. Finally, we also published a technical guide for mass timber buildings up to 12 stories for Quebec. And this was a tremendous help for the designers in Quebec and the authorities having jurisdiction to basically accept these buildings to be built up to 12 stories in Quebec. So as a conclusion, FPInnovations Building Systems Group is one of the leaders in North America in developing solutions for wood and wood hybrid buildings related to structural, seismic, fire, acoustic, vibration, and durability performance. And we are working close with universities, designers, and industry to provide technical information for developing alternative and codified solutions for wood buildings. And finally, 21st century is really experiencing a renaissance in timber construction, and it really feels to be good part of it as an organization and as an individual myself. With that, I will thank you so much for your kind attendance, and any questions that you have will be welcome. Thank you.
Excellent. Thank you very much, Dr. Marjan. Very interesting talk. So I will go through some of the questions that were asked using the chat window. So there was a question by Mustafa, which I think Dr. Gima addressed that, but if you have anything to add to that. So the question is, what is the highest heavy timber building in Canada, and does it have a concrete steel lateral supporting system? Dr. Gima has shared a link that shows the tallest tall mass timber building in Canada. Do you want to add anything to that?
The tallest mass timber building in Canada is the Brock Commons building, the 18-story that was included in this presentation. There are taller buildings around the world. The HOHO building in Vienna, the 22-story building, and also there are 18 and 23-story buildings in Norway as well. What I can mention is that I mentioned in my presentation about the first initiative of National NRCan, Initiative for Tall Wood Buildings. In 2018, they issued a second initiative. So we will have a second wave of tall buildings coming to Canada. Some of them have been already selected by NRCan. Some of them are shortlisted. So definitely in the next few years, we will have 1 or 2 buildings built in Canada that will be taller than 18 stories. We still don't know yet because it's still, from what I know, they received 30 proposals, and now they are shortlisting those proposals, and we will have much more taller buildings in Canada in the near future.
Mm-hmm. Thank you. We have 2 related questions. One is from Dr. Ashraf. Are you aware of high-resolution finite element modeling done to characterize the connections? And related to this, Vinay asks, what kinds of finite element models were done in studying mass timber since the material properties are orthotropic?
Yes, the material properties are orthotropic for timber, and that's why modeling everything timber structure is really different. But what we are using is mostly, I'm just saying for our research, we either used OpenSeas or we use Abacus for modeling of the buildings. And in Abacus, we choose basically, depends on the system, of course. We either choose shell element or plate element or beam element. And then in that element, basically, we are giving different properties in different directions. So the anisotropy of the wood or the product basically is there. It's implemented in the modeling. On the first question, have we done modeling with high precision modeling on the connections? We are working on that. We are also working on high precision modeling, not only from to determine the connection performance, the structural performance, but also to gather structural and fire performance. So that's what we have project on as we speak on that one. And but as you know, modeling of wood has challenges, and we are actually on the forefront of this. We are working with several universities in US as well on this, and hopefully that we'll be able to have some models available in the coming years. It's not easy. It's not easy.
Yeah, for sure. Thanks. Another question is, how do the connectors between the steel moment resisting frames and the CLT panels dissipate energy?
Yes, that's a very good question. And again, I apologize for just throwing out the ideas, but again, that system, of course, we worked 2 years on that, and a presentation can be made on that as only. So basically, you have the gap between the steel beam and a column and the CLT panel. And within that steel gap, you put a connection. That could be a simple connection as a bracket that can be connected to the steel beam and column with certain fasteners, and to the CLT infill wall with, say, nails or screws or whatever. So the part of that connection, the connection between that bracket and the CLT panels, where we put the weak link, where basically that energy dissipation is happening. And by choosing basically the width of that gap, is it 3 millimeter or 5 millimeter or 10 millimeter in some cases, gap, and choosing the fastener on the CLT portion, basically you can change the performance of that system. So if you choose, of course, a higher gap, that means then you have to use a fastener with a higher ductility to be able to reach that 10 millimeter gap in that. So that's why what we did was kind of like performance-based design. And of course, then you have to make sure that that gap is not basically, in some cases, you don't want the CLT panel to touch that steel, because that way you change completely the period of the building and the response of the building. So it's a kind of like iterative solution where you start with a single gap, then try one fastener and see how it goes, and find basically for each different gap what is the best solution for that. That was a very interesting project, actually. I enjoyed it a lot. And the benefit of that project is, for example, instead of using specially designed moment resisting frame with higher R factors, which is always more expensive than if you have a low ductility moment frame. So you have basically lower expense in terms of steel, but then you adding these CLT walls with the connections, you kind of enhance that ductility and energy dissipation.
All right. Thank you very much. A question from Nicole: how does construction of these projects vary from typical steel or concrete structures, and what are challenges associated with it?
Oh boy, I need an hour. Well, wood is, first of all, wood is a very different material than steel and concrete in general, but what I can say is these new engineered wood products or mass timber products such as cross-laminated timber and others, they're kind of helping us in terms of getting the wood into more solid product, more massive product with less variability in any direction. And that kind of helped us a lot to achieve and go to these bigger heights that we have. So how are they different? For example, CLT buildings are different. One of the big advantage of the CLT building compared to concrete buildings is that they can be manufactured, everything can be manufactured in the factory. So you can have your CLT walls, your CLT floors, all manufactured to precise dimensions. Your window openings and other service openings can be pre-cut in the factory. They can be shipped on site and can be erected on site. So for example, the 18-story building at UBC here, so 18 stories of CLT were erected in 9.5 weeks by a crew of 6 to 7 people. So that's huge advantage of CLT buildings, how they are constructed with respect to concrete. So the fast of construction. The other systems of linear type mass timber systems, brace frames, moment frames, and those, they are also using the same principle. Basically, they're all prefabricated and just basically connection are done on site. So in that way, they are kind of more similar to a steel buildings, I would say. But the wall types of structures, such as CLT, they differ significantly from concrete. They're more, if I can use, they're more similar to precast concrete, something like that. That would be my best.
Sure, thank you.
Or prefabricated concrete solutions. Yeah.
Yeah. Question from Mustafa: are heavy timber buildings, I don't know how to read the acronym, I think it stands for glued laminated timber, capable of resisting lateral loads? And if yes, what are the types of connections associated with it?
As I mentioned throughout my talk, in mass timber buildings, in terms of seismic loads and lateral loads, the loads are basically taken care by the element itself and the connection. So I just want to mention, for example, what is the difference between say steel and concrete buildings and wood buildings. If you do seismic design of steel buildings, you want basically your connection to be stronger than the member. In wood buildings, it's completely the opposite. So if you have a glulam column and glulam beam, the connection between glulam beam and the glulam column is your weakest link. So that's where your ductility occurs. That's where your deformation occurs. The beam and the column are always designed to be capacity protected. So basically, there's no damage in those elements. So definitely, of course, glue laminated timber can be used as a column and as a beam. We have thousands and thousands of structures around the world built with those products. But the main part is the connection. So you want basically to have all the ductility in the connection, all the deformation in the connection without failure.
Thank you. Considering reoccurrence of seismic activity and loosening of connections, what is the lifespan of timber structures?
Well, again, in terms of there are two ways how you can talk about lifespan here. Lifespan, if a building on its own, without being attacked by, subjected to an earthquake or other type of severe event, it's definitely let me start this way. We have different types of wood buildings. We have our bread and butter 2x4 construction and 2x6 construction, or as we say, light wood frame construction that can go up to 6 stories. And those buildings are able to basically survive 60 to 70 years. That is their design lifespan. For the mass timber buildings, they're relatively new. We just started building those mass timber buildings about 30 years ago. So the lifespan of these buildings is much longer. It's up to 100 years. And again, that's without any earthquake or any other significant event. If an earthquake occurs, and if the building is designed using capacity design procedure like any other type of a building, then definitely there will be damage to the building in the connection. So those connections will have to be replaced like in the other any other building. And that was the reason why basically I mentioned in my presentation those low damage systems, because we are all very aware that after an earthquake, there is a significant damage in any city. And I'll just mention here the example, the latest well-known example, for example, in Christchurch, New Zealand. They had severe earthquakes, 2 severe earthquakes. And although all the buildings in Christchurch, they performed well according to the code, over 1,000 buildings, they had to be demolished, and they're still demolishing them 10 years after the earthquake. So the average person, the average owner doesn't really understand much about the seismic performance of a building. They think that if the building is built according to the building code that I'm fine. No, you're not fine. The building code just provides the minimum performance. And that's that basically life safety is preserved. So out of the building, we are saying during a severe earthquake, your building will be damaged heavily, but the building should not collapse. So we are designing for collapse prevention. After the earthquake, unfortunately, the building will not be able to be used. And that's why we're focusing now, not only in wood, but in many other areas, towards high-performance buildings, where basically, after the earthquake, the building will be able to withstand and basically be in operational within a few days after an earthquake. Of course, those systems are more expensive, but you pay more to have less downtime after an earthquake.
All right, excellent. Thank you very much. We have a couple of other questions, but unfortunately we are past our time for this seminar. So I encourage everybody who has any questions to contact Dr. Marjan directly through email. I hope you don't mind answering. Yeah,
it will be a pleasure.
Sure. Thank you very much again for your accepting our invitation and for your very interesting talk. And I hope you will give us more presentations in our civil seminars in the future as well. Thank you all for attending this. And I think with that,